Hello everyone and welcome back. My name is Mr. Cobalt and in this video I'm going to be going over Dalton's law of partial pressures. So what is Dalton's law of partial pressures? Well, simply put, it says that the total pressure, over here, the total pressure of a mixture of gases is going to be equal to the individual pressures of those gases. And the individual pressures of those gases is what we call the partial pressure, right? So, because it's a pressure of part of the total. So, remember, these different gases that are mixed together have their own pressures due to that gas. Now, Dalton's law of partial pressure says that if you add up the individual pressures of each individual gas in a mixture, then the total pressure of the mixture will equal those individual pressures. So that's what Dalton's law of partial pressures is saying. So in this case, we're assuming that the gases do not react together, right? So we're not going to put the gases together and all of a sudden they're going to react. That would not that would not work for Dalton's law of partial pressures. Um, so here's a couple of examples to kind of let you know what I'm talking about. So here, the first one is let's say we have these separate containers, same volume, same temperature, everything's the same about these containers except for the gases themselves and the partial pressures of those gases. So same volume container, same temperature, right? So in container one, we have the some gas A, and it's exerting a pressure of 200 kilopascals. So that is the pressure in container A. Container B, same volume and temperature. That gas B is going to be exerting a 500 kilopascals of pressure. And then in container C, again, same volume and temperature. That gas is exerting a pressure of 400 kilopascals. Now, if we took all of these gases and put them all in the same container, same volume, same temperature, then according to Dalton's law of partial pressures, the individual pressures of the gases should add up to the total pressure. So the total pressure in that container would add up to the individual partial pressures of the gases. So 200 plus 500 plus 400 gives us 1100 kilopascals. So that would be the total pressure of the in the container due to the mixture of gases. Now, the second example is more one that we're familiar with, and that is the atmospheric pressure. So, as you know, our atmosphere is made up of a mixture of gases, oxygen, nitrogen. Nitrogen is by far the largest substance that occupies most of our atmosphere. So, most of our atmosphere is nitrogen, and then following that is oxygen. And then we have carbon dioxide, which is very small compared to the other two. And then we have argon, but we also have traces of other gases. But those are the ones that we're going to focus on for this example. So if we think of the atmospheric pressure as the total pressure, then the total pressure or atmospheric pressure would be the total of all of the partial pressures of those individual gases in the atmosphere. So, for example, we say that air pressure, the atmospheric pressure, is equal to the total pressure. And though that total pressure is made up of the partial pressure of oxygen, the partial pressure of nitrogen, the partial pressure of carbon dioxide, and the partial pressure of argon. And then there are traces of other gases, but we're ignoring those. And so if we take the numbers here, right? So let's say that the partial pressure of oxygen is 149 millimeters of mercury. And then nitrogen is 590 millimeters mercury. Carbon dioxide would be 3 millimeters mercury, and argon 8 millimeters mercury for the partial pressures, respectively. And then, so if we add those together, we add the partial pressures, then the atmospheric pressure would be 750 millimeters of mercury. And so that gives you an idea of what we mean by Dalton's law of partial pressures and a couple of examples to hopefully uh, clarify anything. So the next thing I want to talk about is that it doesn't matter the type of gas you have. What do I mean by that? In just a moment. Okay, so as I said before, the type of gas does not matter. It doesn't matter for Dalton's law whether you have carbon dioxide, whether you have oxygen, whether you have argon, whether you have any gas whatsoever. That doesn't matter. So all that matters is the temperature, the volume, the pressure, basically gas laws, right? So as an example, I have here 3 containers. We'll pretend that they are the same size, even though they may not look it. So here, all of these containers are 5 liters, and the temperature is all the same at 20.0 degrees Celsius. And so we'll see here that if you plug in the values, right? So here we have 1.7 moles of just helium in this one, right? So if you use PV equals nRT, plug in all the values, right? You plug in the volume liters, you plug in the temperature in Kelvin, of course, you got to convert this to Kelvin. And then you plug in the number of moles, right? And you solve for pressure, then you'll get 8.4 atmospheres as your answer. Now, if you have a mixture of gases, you can have, for example, here you can have 0.75 moles of hydrogen, 0.75 moles of helium, 0.725 moles of neon. You could do a couple of things in calculating this. You can plug in the moles individually into your ideal gas law, right? PV equals nRT, and then find the partial pressure for each of these. So do the calculation 3 times using your ideal gas law, and then add up the partial pressures of all of those gases, and it should add up to 8.4 atmospheres. The other way you could do it is just add up all the moles of your gases to get the total pressure and plug the total pressure into your ideal gas law and do the calculation once. You should find that you'll still get 8.4 atmospheres of the pressure. Now, did the identity of the gases factor into that? No. Nowhere in the equation does it require you to put in the identity of your gas. All it matters is what the temperature is, the pressure, the volume, and all that stuff, the number of moles. Just the number of moles is really what's important here when we're talking about a mixture of gases. And so again, here we have a different set of gases with a different number of moles. And if you add up the number of moles, you still get 1.75. So the number of moles stays the same. You plug that into your ideal gas law, and you get the exact same pressure out of the equation. So the type of gas doesn't matter, right? So because the reason is because as long as the temperature, volume, and the temperature and volume are the same, and the number of moles are the same, then you'll always get the same pressure, right? So that's it for this section of the video. The next thing I'm going to talk about is how you can get the partial pressures from what are called mole fractions. And I'll talk about mole fractions right now. Okay, so let's talk about mole fractions. So you can use mole fractions to find partial pressures. So let's remind ourselves that in a gaseous mixture, a gas's partial pressure is the one that the gas would exert if it were by itself in the container. So the mole fraction in a mixture of gases is going to determine each gas's partial pressure. And let me explain why that is. So when we're talking about mole fractions, we're talking about a mixture of gases. So we said that according to Dalton's law, the total pressure of all the gases in the mixture is equal to the individual partial pressures of the gases as if they were by themselves in the container, right? So when we're looking at the moles, we saw before that the number of moles is related to the pressure in the container, right? So we saw before that it didn't matter what type of gas you had, as long as the total number of moles of each of the gases, no matter what the identity of the gas was, added to the same number of moles, you got the same pressure under the same conditions of volume and temperature, right? So if we're assuming here that volume is the same, temperature is the same, and of course the ideal gas law constant is the same under those conditions, then just as the total pressure is equal to the number of partial pressures, that is also going to be the case, of course, that the total number of moles that gives you that total pressure is a result of the number of moles that you have. So each number of mole is going to be proportional to the pressure of the gas, right? So this is under the conditions of same volume, same temperature, and under those conditions, the number of moles of the gas is proportional to the pressure, the partial pressure. So we can use that in this way. So the mole fraction, what is the mole fraction? The mole fraction, which is symbolized by this chi symbol, it's like an X. Greek symbol chi is this X here. So the mole fraction is going to be the mole fraction of gas 1 is going to be the moles of that gas per total moles given. So again, mole fraction. Mole fraction is that fraction out of the total. What fraction of the total it pertains to that particular gas? So if we're looking at a mole fraction, then we want to know the moles, the fraction of moles that pertains to that gas out of the total. So the mole fraction of gas 1 is the moles of gas 1 pertaining to the total over the total number of moles. Same for the mole fraction here. The mole fraction 2, chi, the x2, the mole fraction of gas 2 is the number of moles of that gas 2 over the total number of moles, out of the total number of moles given, right? So here we have a fraction of moles of gas 1 over the total moles, and here the mole fraction is moles of gas 2 over the total moles. Now, because this is proportional because the number of moles is proportional to the partial pressures under constant volume and constant temperature, then the mole fraction, and of course, we can get this if you use the ideal gas law and you plug in and you solve, you put in the ideal gas law, solve the ideal gas law for N and plug this in for N, everything cancels out except for pressure. So, so the mole fraction of number of moles of gas 1 over the total moles is also going to be equal to the partial pressure of gas 1 over the total pressure. So the mole fraction is going to be equal to the ratio of the partial pressure of gas 1 over the total pressure. And the same thing for the mole fraction of gas 2. The mole fraction of gas 2 is also going to be equal to the partial pressure of gas 2 over the total pressure, and etc. for any other gases in the mixture. And so now what you can do is you can take this relationship here and solve for the partial pressure of gases 1 and 2 and so on. So the partial pressure of gas 1 is going to be equal to the total pressure multiplied by its mole fraction. Again, the mole fraction is this here, the number of moles of gas 1 over the total moles. And so for the partial pressure of gas 2, that's going to be equal to the total pressure multiplied by the mole fraction of gas 2, which is, again, this relationship here, and etc. for any other gases in the mixture. So now we can use this equation to find the partial pressures of each gas in a mixture. So next I'm going to go over a few problems and show you how to use this to solve gas law problems. Okay, so here's problem number 1. The total pressure of a mixture, and they're giving us the mixture of 3 moles of helium and 4 moles of neon. The total pressure of this mixture is 97.4 kilopascals. So they want us to find the partial pressure of each gas. So they're giving us the moles of the individual gases, and so we can total that and find the total moles. And so therefore we can use the mole fraction. Why? Because they're giving us the total pressure as well. So we can use the equation of partial pressure of the gas is equal to the total pressure multiplied by the mole fraction. So if we write out the equation, so the pressure, the partial pressure of, say, helium is going to be equal to the total pressure multiplied by the mole fraction of helium. And what is the mole fraction? So the mole fraction of helium, let me write that better. So the mole fraction of helium is going to be equal to the number of moles of helium divided by the total moles. Well, what is the total moles? Total moles is 3 moles plus 4 moles. That's 7 moles. So we know that the number of moles of helium is 3. So 3.0 moles of helium over the total, which is 7.0 moles. So there's our mole fraction. And so we can do the same equation here for neon. So the partial pressure of neon is equal to the total pressure multiplied by its mole fraction, the mole fraction of neon. And again, the mole fraction of neon, let me write it over here. So the mole fraction of neon is going to be equal to, again, the moles of neon divided by the total moles. So the moles of neon over total moles. Well, let me make sure I get this right. Get this on screen. So here we go. So here we have the mole fraction of neon is going to be equal to the moles of neon over the total moles. And that's, again, going to be equal to 4.0 moles over 7.0 moles. Okay, so then all we need to do is plug in the mole fraction for each of these into our equation and plug in the total pressure for each of these. So then if I continue down here, that means the partial pressure of helium is going to be equal to the total pressure, which is 97.4 kilopascals, multiplied by the mole fraction of helium, which is 3.0 moles over 7.0 moles. And the mole fraction is a unitless thing because, of course, the moles cancel out. And, of course, this is going to give you an answer in kilopascals. And so the answer here is going to be, let me make sure I got this right. Yep. It's going to be 41.7 kilopascals. And then I can do the same thing for neon. So the partial pressure of neon is going to be, again, total pressure, which is 97.4 kilopascals, multiplied by the mole fraction of neon, which is going to be 4.0 moles of neon over 7 total moles of their mixture. Again, these moles cancel out, and you're left with a 55.7 kilopascals for neon. And so that's how you use the mole fraction to find the partial pressures of a mixture. Okay, next I'm going to do another practice problem, which is going to involve Boyle's law. Okay, so I misspoke. This one doesn't deal with Boyle's law just yet. That'll be the next one. But here we're going to deal with molar conversions. So you could add molar conversions to your problem and still solve it the same way. So if you're given a problem that doesn't have moles and you want to use the mole fraction to find the partial pressures, you got to have to first convert your grams to moles using molar mass. So it's just one extra step or a couple extra steps until you get to where you want to go. Okay, so here we're given in this problem 80 grams each of helium, neon, and argon, and they're all in a container, so they're mixed together, and they're giving us the total pressure is 780 millimeters mercury. Find each gas's partial pressure. So in order to get the mole fraction, we're going to need to convert to moles first. They gave us the total pressure, so if we could find the mole fractions of each, then we can use the mole fraction and the total pressure to calculate the partial pressure of each gas. So they gave us the mass of each gas. So convert that to moles, and we'll have our mole fraction. So let's take we take 80 grams of helium, and the molar mass of helium is 4. We're going to round it to make our calculations easier. So basically, we have 4 grams of helium per 1 mole of helium. So the grams of helium cancel out, and then 80 divided by 4 gives us 20 moles of helium. Do the same thing for neon. So neon, we have 80 grams of neon over 1. And again, we're going to use our molar mass of neon. So for neon, that's going to be 20 grams per mole. Again, we're rounding our numbers to make the calculations easier. So that's going to be 20 grams of neon for every 1 mole of neon. So grams of neon cancel out. And so that's going to give us 4 moles of neon. And then finally we have argon. Where's argon? Yeah, argon here. So we have 80 grams of argon over 1. And again, we're going to use the molar mass of argon, which is 40. So 40.0 grams of argon for every 1 mole of argon. Grams of argon cancel out. That's grams. Grams of argon cancel out. And here we have 2 moles of argon. So the total number of moles is 26. So the mole fraction of helium, so again, the mole fraction of helium is going to be the moles of helium divided by the total. So that's going to be moles of helium divided by total moles, which is going to be 20 over 26, 20 moles over 26 moles. The mole fraction of neon, same thing. Moles of neon divided by the total moles. So moles of neon over total moles, which in this case is going to be 4 moles over 26 moles. And argon, same thing. So we have the mole fraction of argon, which is going to be the moles of argon over total moles, and that's going to be 2 moles over 26 moles. Okay, so we've got our mole fractions. We got the total pressure of the mixture. And so all we need to do now is just multiply the mole fraction by the total pressure. So we take for the partial pressure of helium, that's going to be the total pressure, which is 780 millimeters of mercury. Multiply that by the mole fraction here, which is going to be 20 divided by 26. And there we get our answer of 600 millimeters of mercury. And then the partial pressure of neon is again equal to the total pressure, 780 millimeters of mercury, multiplied by its mole fraction, which is 4 over 26. So 4 moles over 26 moles. Calculate that out and you get 120 millimeters of mercury. And then finally you do the argon. So the partial pressure of argon is equal to 780 millimeters of mercury multiplied by the mole fraction of argon, which is 2 over 26. And again, that's going to be equal to 60 millimeters of mercury. And so here, if you add all these up, you get 780 millimeters of mercury. So that's how you would use molar conversions to help you get your mole fractions and to get your partial pressures. So now I'll go over a problem where you are going to do Boyle's law. But I'll have to say that for another video because that's kind of a separate thing. And so I hope this helps. If you enjoyed this video, please by all means like this video, hit that like button right there, share the video with your friends, subscribe to my channel, hit that notification bell so you'll be notified by other videos. But when you do, please make sure you click all. So click on that notification bell and then click all. That way you'll be notified by all videos that I put out. And also put a comment down below in the comment section. Let me know what you think. Ask me questions if you got them. I'd love to hear from you. Thanks for joining me and have a great day.